The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Desiree Schell. This week we're diving back into the fascinating and sometimes intimidating world of numbers. A little later, guest host Rachelle Saunders speaks to science writer Brian Clegg about his book, A Brief History of Infinity, The Quest to Think the Unthinkable. But first, we're going to take a detour through a subject that we don't talk about very often here on Skeptically Speaking. The world of sports. I'm here with physicist, author, and an occasional actor-director, Aaron Santos. Aaron has a bachelor's degree in physics from MIT and a PhD in physics from Boston University. And he's currently serving as a visiting assistant professor of physics and astronomy at Oberlin College. We interviewed Aaron in January of 2010 about his first book, How Many Licks? Or How to Estimate Damn Near Everything. Today he's here to talk about his new book, Ballparking, Practical Math for Impractical Sports Questions. Welcome back to the show, Aaron.
Hi, thanks for having me.
Now, ballparking is sort of a follow-up to How Many Licks, right?
What happened was I had gone to Running Press, who's been very good to me, and I said, I really want to do a second book. And I said, I have this great idea for, I want to make a science fiction book. We're going to call it The Math of Khan, and it's going to be all sorts of science fiction-y numbers. And they're like, yeah, that's great. We really want you to do a sports book. So I was like, all right, well, that sounds good too. But I had tons of fun with it. I played sports when I was younger and up through college, and I forgot that it was something I actually enjoyed.
Well, maybe before we get to the math in the sports and the such, tell us what a Fermi equation is so people have some background here.
Sure. So Enrico Fermi was an Italian physicist who would go up to his students and he would say, how many piano tuners are in Chicago? And on the spot, these students would have to come up with estimates for whatever question he might happen to ask. So the idea is that using very little information, basically just what you have in your own head, you should be able to come up with a reasonable estimate for just about any question you can answer. So that's really what a Fermi estimate is. We've kind of taken his name, and physicists are known for doing these kinds of problems all the time.
So this is an emphasis on the estimate.
Yes.
It's not used for precise measurements.
No, this is a first step in. You can kind of think of it as an idea filter. I actually like to think of it as kind of a skeptic's tool, because it's great for detecting BS. Because if a number is way off, you can tell pretty quickly just by doing some math in your head.
And I'm assuming the more accurate your estimates for each variable are, the closer your final result will be to reality.
That will, of course, be the case. One thing that's kind of nice, though, is even if all of your numbers are a little bit off, if you throw enough numbers in there, they'll tend to average out a little bit. So even if individual numbers are a little bit off, the end result sometimes is still pretty good.
So would you say that the Drake equation is maybe the most famous example of a Fermi estimation?
Probably, yeah. I mean, I would say either that or the piano tuners one. The Drake equation, I think, I think it's the most famous one that people have used in scientific papers. I'm not sure how seriously anybody really takes it. So for the people who don't know, the Drake equation is estimating the probability that there's life somewhere else in the universe. And it takes into account things like the number of planets and how many are Earth-like and so forth. So using something that we in principle should have no idea what the answer to, you can still come up with some reasonable estimates for probabilities and things like that.
Now, I just want to point out, because I love this from the last time you were on, you used a Fermi equation to estimate how long it would take our staff to suffocate if we got locked in our old studio at CJSR. I love that. And just for anybody that doesn't remember back that far, because it was a long time ago, we used to actually broadcast out of an old bank vault. So it wasn't actually an impossible scenario. You actually gave us 2.5 hours to live. I do remember that.
So there you can plan ahead. So at least your listeners will get 2.5 hours of good programming, and you can go from there.
You're a good man. You're listening to Skeptically Speaking, and I'm Desiree Schell, speaking to physics professor Aaron Santos about his new book, Ballparking, Practical Math for Impractical Sports Questions. So I do want to talk about some of the equations in the book, because they're hilarious. But first, I'm curious, are you actually interested in sports, or was this just something that your publisher pushed on you then?
No, I very much. I still follow baseball a bit. I've been trying very hard to quit being a baseball fan, and the Red Sox have tried really hard to make me stop this year. But I keep coming back. I don't know why. I think whenever you're born in around New England, your parents just, it's like right when you come out of the womb, they start giving you Red Sox stuff, and then there's no real escaping it. So I'm a big baseball fan. Became a little bit of a hockey fan as soon as I moved out to Michigan, and other than that, I follow sports for the most part, but not too religiously.
Well, I was wondering, because this is one of those things that I love, sort of using one idea to get people interested in science and math, using sports to get people interested in science, or using art to get people interested in science. So even if that wasn't your idea, your publishers are brilliant.
Their scorecard is much better than mine is.
Okay, so let's walk through a couple of the estimations that you do in the book.
Sure.
Now, because I am Canadian and I am legally obligated to talk about hockey at least biweekly or face imprisonment, let's talk about the estimations that you've done on how much the NHL has saved on toothpaste.
So for a problem like this, you think, all right, well, let's say I watch some sort of NHL game. Let's say I'm watching the Maple Leafs, and I can sit back and I can count, roughly how many players are missing teeth. And I say, all right, well, what's the average number of players on a team that are missing teeth? How often do I think a player might lose a tooth? Over the course of the year, how many teeth have been lost over NHL history? How many teeth have been lost? And it was, once you've lost a tooth, presumably you don't have to brush that tooth anymore. So I forget the exact numbers, but it was something like over $1 million that could have been saved on toothpaste throughout NHL history. If you just add up all of the teeth that have been lost.
You realize I showed this to a number of non-science hockey fans, and they were duly impressed.
I hope so, because that was a hard one. I was pretty happy that I could come up with that one.
Okay, we have to do baseball because we also have a large American fan base. So, major leagues and rat poo. This is great.
That was not what I was expecting was going to come out. So when I was in middle school, there was a rumor flying around. We used to get hot dogs for lunch because we went to a very healthy American school, and there was a rumor going around that hot dogs allowed up to 5% of the hot dog to be rat droppings. So the question is, all right, if that's the case, ballpark franks are a big popular food in Major League Baseball stadiums. How much rat poo gets eaten each year? So if you go through and you figure, all right, well, each hot dog has 5% rat droppings, and you assume, a certain number of people have, a certain percentage of people eat a hot dog at a major league game, and then you figure out, well, what's the attendance at a game and how many games are there? You can calculate that about 54 tons of rat droppings are eaten each year. So it's not a very happy thought, but that's a lot of rat poo.
See, I felt like I started out with hockey, and then I went to baseball, and it was kind of an American diss right there because it's not a very Canadian sport. So I'm sure I'm going to get emails about this. That's helpful. And one for everyone. Let's go to basketball and Wilt Chamberlain's STDs. Do tell.
In his autobiography, Wilt Chamberlain claimed that he had slept with over 20,000 women. Now, there's been various estimates of what exactly this would entail. It's something like sleeping with an average of 1.5 new women every day. But that begs the question, how many STDs would you catch if you were actually to go out and if you were actually sleeping with this many people, how many STDs would you catch? And it depends a little bit on what assumptions you make. So Wilt Chamberlain was around mostly in a time before AIDS. So you figure he probably wasn't using too many condoms. And if you assume, all right, well, there's 20,000 women, and you assume a certain STD transmission rate, I think the final number was, if you assume no condoms, it's something like 3,000 STDs, and if you assume condoms, then it's less than that. I think it's something like 30, or it's between like 30 and 300 STDs. Again, I forget the exact number. But it's basically the moral equivalent of Wilt Chamberlain running around through the streets screaming out, "I have herpes."
Okay, so A, you, and B, you have an interesting job, sir. This one that you've created for yourself. It's
never a dull moment when you're a physicist.
Well, that was all very disturbing on many fronts. Aaron, thank you again for being here.
Thanks for having me. This was it's always a pleasure.
You'll find links to Aaron Santos and his book, Ballparking, Practical Math for Impractical Sports Questions, on our website at skepticallyspeaking.com. And if you'd like to listen to our interview about how many licks, which was hilarious, you will find that on the episodes page at episode 41. Up next, guest host Rachelle Saunders speaks to science writer Brian Clegg about his book, A Brief History of Infinity, The Quest to Think the Unthinkable. That's right here on Skeptically Speaking, after this.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for regular Skeptically Speaking host Desiree Schell. Today I'm joined by Brian Clegg, author of many popular science and math books, including The God Effect, In-Flight Science, How to Build a Time Machine, and his most recent books, The Universe Inside You and Gravity. Brian has degrees in natural sciences and operations research and spent 18 years working at British Airways before transitioning to a life as a science writer and business consultant. Today we'll be discussing his book, A Brief History of Infinity, The Quest to Think the Unthinkable. Welcome to the show, Brian.
Thanks for having me.
So I'm curious, what got you interested enough in the concept of infinity that you decided, I'm going to write a book about this?
It really goes back to when I was in high school, and we had a very inspirational math teacher. He was a young guy. He was probably only 7 or 8 years older than the students. And he really got us excited about math, and particularly introduced us to ideas like infinity and infinite series. And there was one particular example. He talked about a frog sitting on a lily pad, and that this frog would basically, say, jump perhaps an inch, and then its next jump would be half the size, so it'd just be half an inch, the next jump half the size again, quarter of an inch, and so on. And what he said was that this frog could jump an infinite number of times, and it would never get off the lily pad, because that inch plus a half inch plus a quarter inch and so on, you could go for an infinite set of times, and it would only move 2 inches. And it just so amazed me, this idea that you could add together an infinite set of jumps and it still would only move 2 inches. It stuck with me all these years, and when I started writing books, it was something I really wanted to come back to find out more about and to explore further.
One of the things I really like about A Brief History of Infinity is the balance you provide between mathematics and history. You really give us equal amounts of each here. Why did you decide to delve into the history of the people involved as much as the concept itself?
I think it's really important if you're trying to get quite complicated concepts across. So, whether I'm writing about math in this case, or if I'm writing about quantum physics or something like that, things that people perhaps are a little wary of, I think it helps to make them approachable if you find out a bit more about the people involved. It just makes the subject more interesting, but also more approachable, easier to get into it without it perhaps being quite so scary.
So if you had to define infinity right off the bat before we get started, how would you do it?
It's a difficult one, and people have struggled with it for a long time. I think one of the best ways of saying, trying to imagine what infinity is somebody said, okay, imagine something finite. You can think of something finite. Well, it's something that isn't that. And I know that's a bit trite, but basically the idea of something that it goes on forever, that doesn't have an end, that doesn't have boundaries, is where you're getting into the concept of infinity.
You actually open your book by talking about young children's fascination with really big numbers. In particular, you talk a lot about the Google. Or a Google, I suppose. Why do you think huge numbers and, at the end of the day, infinity captivate us so much?
Well, I think in some ways, and certainly it's true of children, it's almost a sort of sense of power that if you can name something, you have a bit of a control over it. And so if you can give a name to a big number, then somehow you're that little bit clever, you're somehow special. And the Google, which is basically just one with 100 zeros after it, I think is quite interesting because the name did actually come from a 9-year-old child. There was a mathematician who was supposedly had written this number on a blackboard. I think this is totally rubbish. I can't imagine anybody would actually sit there and write out by hand one with 100 zeros after it. The story goes that Ed Kasner, who was this mathematician, was working on it, and his little nephew called Milton Sirota was looking at the board, saw him this big number, and said, sort of, "Uncle Ed, that looks like a Google." And the name came from that. I think it's much more likely actually he asked his nephew, what would you call a really, really big number? And he came up with this word. But even so, it has that sort of childish delight to it.
Now, when we think of infinity, we tend to think of really, really big things, like the idea that the universe could be infinite. But the concept of infinity also comes into play when we're talking about infinitely small things or the spaces between things.
That's right. And in some ways, I guess the first practical approach, the practical use of infinity most of us come across is if we do calculus at school or whatever. So basically the idea that you can add together lots of incredibly tiny things that are so small that they effectively disappear towards nothing at all. And you can add those together and make something useful out of them, so that the calculus that's used to work out I don't know, the rates at which things accelerate or to work out areas, it's used all the time by engineers and scientists, is all really based on working with tiny values that are disappearing towards nothing at all.
You're listening to Skeptically Speaking with guest host Rachelle Saunders, and today we're talking about the history and paradoxes of infinity with science writer and author Brian Clegg. Now, the ancient Greeks were actually some of the first to really begin digging into infinity and try to understand some of the paradoxes there. And one of the main ones was Zeno, who ventured into the world of infinity by considering some paradoxes around distance and motion, I believe.
Zeno was part of the school of Parmenides, that believed that things like change and movement were an illusion, that they didn't really exist. But we imagined them. And they tried to prove this by coming up with a set of paradoxes that seemed to show that change couldn't happen the way we thought it did. Most of these have been lost, but a few of Zeno's paradoxes have come through to us. And I guess actually probably the best known one, two really. One's about an arrow, which is basically the idea you've got to imagine we've got an arrow flying through space. And what Zeno said is, okay, let's imagine we freeze it in time, which is pretty amazing concept, really, when you think they obviously didn't have movies or anything like that. It wouldn't be used to stopping movement. But you imagine a moment in time, that arrow is suspended in space, and let's imagine there's another arrow that's not moving at all. How do you tell the difference between them? It was that kind of paradox. So basically, one's moving, one's not. But in that moment of time, there seems to be no difference between them. And that was the kind of thing that we're using. But the one that's particularly, I think, important when we think about infinity was a paradox involving Achilles and the tortoise. And the idea of this, it's actually very similar to the frog on the lily pad that I mentioned earlier on, is that Achilles is having a race with the tortoise. And let's say he runs twice as fast as the tortoise. And he gives it a lead because he's a hero. After all, he's going to give it a chance. So the tortoise sets off, maybe it goes a foot, and then Achilles sets off. And obviously he catches up with it very quickly. He covers that foot. But in that time, the tortoise has moved on. It's moved on another 6 inches. No problem. He covers that 6 inches very quickly. But by the time he gets to that point where the tortoise was, it's moved on again. It's another 3 inches ahead of him. And the paradox says he's never going to catch the tortoise because every time he gets to the point it's reached, it's moved on. And what we see here, just like the frog on the lily pad, actually, is one of these series of numbers that if you add them all together, if it's moved a foot and then 6 inches and then 3 inches and so on, you can put together an infinite set of those and it will only ever move 2 feet. And that's the point where, in practice, he actually powers past the tortoise. But it certainly made an interesting way of thinking about infinity and its implications.
Now, the Greeks actually weren't really well equipped to deal with infinity, in part because their numbering system didn't work well for large numbers, and they also didn't have a number system for fractions or decimals. How did this make things tricky?
Well, the fractions side particularly came in when you were dealing with these kind of series of numbers. If you are trying to add, we can imagine adding 1 to a half, plus a quarter, plus an eighth, and so on, and have a series of numbers like that. But for the Greeks, the fractions were represented by effectively the character itself with just a little dash. So basically, if you wanted to say what we'd call a quarter, they'd write the character 4, which is actually just the 4th letter, with a little dash over it. Because it didn't have any structure, where when we write a quarter, we've got 1, and then the line separating them, and then the 4, we can see the relationship between the two. That wasn't at all obvious. And using fractions, if you had to add 2 fractions together, was really quite complicated. In fact, they sold tables where if you wanted to add 2 fractions together, it told you what the result was, because it was very difficult to work out. So that was one problem they had. But the other one you mentioned, I guess the biggest one in thinking about infinity, was that their number system only went up to 10,000. A myriad, 10,000 was the biggest number in the system. And they could talk about a myriads, so 100 million, but that was about it. And that was where Archimedes, the guy I guess is most famous for sort of jumping out of his bath with no clothes on and running around shouting Eureka, came in, because he wrote a book where he basically expanded the number system so that he could count how many grains of sand it would take to fill the universe.
Wow. Did he actually finish that calculation?
He did, yeah. It was really interesting for 2 reasons, really. Partly because of the math. So basically what he was doing is extending that number system and making it work to any scale. But also it's interesting, I guess, as a historical note, because in thinking about the size of the universe, he actually says, he works out roughly how big the universe is. And he actually makes a pretty good guess. The size he estimates is about the orbit of Saturn. And when you think what they meant when they described the universe was basically the solar system, that wasn't a bad guess on the size. But the really interesting thing is that he says, this is how big the universe would be, assuming it is the way we think it is, with the Earth at the center, because at the time they thought the Earth was at the center of the universe and the sun went around it. But he also says there's this little book that's come out that suggests, in fact, the sun's at the center of the universe, not the Earth. And if that's the case, here's another calculation that makes the universe a bit bigger. And that's actually one of the earliest references we have to this idea that maybe the sun's at the center of the universe rather than the Earth.
Interesting. I know that there was a geometric problem that bemused a lot of the Greek philosophers, which was the squaring the circle problem.
That's right, yeah. The squaring the circle was so much a problem for the Greeks. They actually had a name. I'm afraid I can't come up with it off the top of my head, but there was a name for the act of trying to square the circle, which was basically trying to come up with a square that had the same perimeter as a circle, of a particular circle. And the problem they had there was, of course, they didn't know about pi. We now know that the circumference of a circle is 2 pi r, where pi is this number 3.14159 and so on, that just goes on forever and never actually will repeat itself. They weren't aware of that, and because of that, they were attempting to do something that basically was impossible.
So pi is actually what's called a transcendental number. What does that mean?
Well, it's really sort of the second stage away from an ordinary conventional number. They were very familiar back then with ratios. So the idea of you take one whole number, and divide it by another whole number. But what they weren't particularly familiar with, certainly to start with, was the idea of irrational numbers. So the simplest example of that is if you think of a square that's got one unit on each side, how big is the diagonal of that square? And Pythagoras, of course, and his predecessors came up with this concept of Pythagoras' theorem, where you find the diagonal of a square or the hypotenuse of a right triangle, basically by squaring the two sides and adding them together, take the square root. So here we've got two sides, one each. 1 plus 1 is 2. We take the square root of that, square root of 2. That's how big the diagonal is. And with a little bit of logic, it only takes about a page of logic, you can actually prove that number, the square root of 2, is not a ratio of any two whole numbers. It's what we call an irrational number. Now, the interesting thing about that in terms of Pythagoras is his school believed that the whole universe was built on whole numbers, that numbers were at the heart of the universe. And the legend is, I don't know if this is true or not, but the legend is that somebody called Hippasus let the cat out of the bag and told people about this diagonal of the square being not rational. And they were so horrified by him letting it out that they're supposed to have taken him out in a boat and drowned him for letting people know. So that's irrational numbers. Transcendental numbers just take things one step further, something like pi, where it's not only not a ratio of two whole numbers, but it can't be calculated by using a formula that's less than finite, less than infinite rather. You have to have some form of formula that goes on forever to calculate it. You can only approximate to it. You can never write down the actual final value.
What I find really interesting about pi is that it goes on sort of literally forever. It's a number that we all use in grade school, that we all, use on a regular basis to calculate with, but it can never be exact. Is that correct?
That's right. We've calculated pi with computers to billions of decimal places, but in the end, it is literally infinite in length. If you wanted to write it down perfectly, your number that you wrote down would have to be infinitely long, simply because it doesn't repeat. If you get a simple decimal like, a third, so it's 0.3333, we can say exactly it's threes all the way. But with pi, it's not like that. There's no point where you can actually say, okay, this is where we can stop, we've calculated it, and the rest will just repeat itself. It's not like that.
You're listening to Skeptically Speaking with guest Brian Clegg, author of A Brief History of the Infinite, and we're discussing the various ways mathematicians and philosophers have tried to understand the infinite over the centuries. Now, in your book, you also talk about a work by Galileo, written in the form of a conversation between three characters that includes a whole, actually quite mind-bending section about thinking about infinity, including a physical two-wheeled machine that, when you think about it, seems to be doing the impossible.
Galileo actually was a really good writer of science. We tend to think of heavy-duty scientists like Galileo as being difficult to understand, but he was actually quite good at writing books that explained his ideas. And in this book, which is called On Two New Sciences, he wrote it after his trial, so this was while he was under house arrest. It really is his view on physics. And as you say, he almost has a little detour. His three characters in the book say, we've got plenty of time, let's just think about something. Let's think about infinity because it's kind of interesting. And he comes out, as you say, with this concept of these machine with two wheels. And it's a bit difficult to visualize, but what you can imagine is basically we've got two wheels, a small one and a big one. The small one's fixed to the front of the big one. And let's say they're six-sided wheels, so they're hexagons. And each of those two wheels sits on a rail. So basically the small one's sitting on a rail that's a bit higher up, so it's sitting on it. The big one is sitting on another rail. And what we do is turn the wheels by one side. So basically it's moved off one side, rolled onto the next one. Now, of course, the big wheel has bigger sides than the small one. And so what we're doing is moving the whole thing forward by the length of one side of the big wheel. And you might wonder, and Galileo does say this, why the little wheel manages to move with the big wheel, even though it's rolling along its own rail. And the way it does it is by actually lifting off the rail partway through. It does a jump so that it can go as far as the big wheel does, because they're fixed together. Now, the clever thing Galileo then does is say, let's imagine we've got more and more sides on these wheels until they become circles. So effectively got an infinite set of sides, and they become circles. And if we do the same thing, something really weird happens, because the little wheel still has to catch up with the big wheel. It still has to keep up with it. And yet it never lifts off its rail, because it's now a circular wheel. It's rolling along its rail quite happily. So how does it manage that? And the way Galileo explains this is to say what's happening is it still is jumping off the rail, but because it's got an infinite set of sides, because it's circular, effectively what it does, it has an infinite set of infinitely small jumps. So you never notice them, because they're becoming infinitely small and they can fill in any gaps. And it is quite mind-boggling. In fact, he has a character in the book called Simplicio, and his job is basically to say, I don't really understand this, so that it can be explained, and he's really confused by this. But Galileo manages to sort it out and help him to understand a little bit more about infinity.
This is a really confusing idea, because it is something you could actually see and measure, and it doesn't really make sense without sort of the infinite involved in this.
That's right. It is actually bringing, if you like, infinity into something physical. Now, in practice, of course, no wheel is perfectly circular. So in practice, there will be little imperfections in a real physical wheel. That means you're not actually probably technically dealing with truly infinite. But in a mathematical imagination of a wheel that's perfect, then literally you are having an infinite set of little jumps that are infinitely small, that enable that small wheel to keep up with the big one.
So as we mentioned before, infinity plays a huge role in calculus that is used every day to solve real-world engineering problems. And without dealing with the infinite, I don't think calculus works, does it?
That's right. I mean, calculus in a way is a bit like these wheels, in that what you're dealing with is you're looking for a very small change in something. So if you imagine a simple example of something you might do in calculus is to measure the way something is changing. And you might imagine a curve that describes how something changes. Now, it's very easy to see how something's changing if it's just moving in a straight line, because basically what we can say is, you imagine, for instance, you're measuring the slope of a hill. If it's a nice straight line, that hill, it's very easy to measure the slope, because you measure just how far it goes up, how far it goes across, divide one by the other, and you get the slope. And that's fine. But what if it's curved? That's where calculus comes in, whether it's the slope of something or whether it's acceleration or whatever. The way calculus works is to say, imagine looking at a smaller and smaller and smaller part of that curve until you've got a really tiny part that is effectively pretty well a straight line, and we can then apply this exactly the same method to that tiny little straight line, and then we add all the tiny little straight lines together. We bring them together just as Galileo did with those little jumps in the wheel. And to make it perfect, we've got to make those parts smaller and smaller and smaller till they effectively disappear. So calculus is dealing with an infinite set of infinitely small things to make them work together.
The story of the birth of calculus is a really interesting one, which I don't think a lot of people know. And it involves actually a fight over who did it first, and escalated into a really quite nasty battle between Newton and Leibniz.
Newton came up with the idea, he called it the method of fluxions. And he probably actually came up with it first, but when he was in his 20s. But he didn't write anything about it for a long time. And at the same time, Leibniz was working on this over on the continent of Europe, and he published his ideas first. Now, Newton had sent some thoughts to Leibniz, but he'd done it in a coded way, really just as a way of trying to prove that he thought of these things first. And he got somebody to accuse Leibniz of cheating, of copying his work, of plagiarizing it. And as you say, it became a really big fight. And the bizarre thing is that the Royal Institution, the Royal Society in Britain was already established. Newton was one of its early founders as a scientific society, and it got together a group of men who would decide who came up with the idea first of calculus, whether it was Newton or if it was Leibniz. And the interesting thing about that is that it wrote a report written by the president of the Royal Society that decided that Newton got there first, and yet Leibniz still wouldn't accept it. But in some ways, this wasn't totally surprising, because the president of the Royal Society was Sir Isaac Newton. He actually wrote his own report deciding that he got there first. And the result of that, literally for 100 years, mathematicians in Britain and the rest of Europe basically didn't talk to each other. There was so much rancor that came out of this argument over calculus.
So this is sort of like a Family Feud-esque battle that raged for quite a while.
Yeah, and the funny thing is, I mean, all the evidence is that they did come up with it totally independently. As I say, Newton probably got there first, but Leibniz's method was actually easier to use, more practical, and his symbols and approach are the ones we still use today, rather than Newton's. The other thing that's quite interesting in this battle is actually there was a third figure involved, which was Bishop George Berkeley, who was a philosopher and mathematician as well as being a bishop. And Berkeley actually suggested that both of them must be talking rubbish, because basically of this concept that they were using a quantity that got smaller and smaller and smaller until it disappeared. He called it the ghosts of departed quantities, the idea that they were using things that were effectively zero. In fact, they were even dividing one of these things by another. So effectively, they were dividing 0 by 0, which these days mathematically we would say has no value. And there actually was a genuine concern. He wasn't just being difficult. There was something technically wrong at the time with calculus. It worked, but mathematically it was on very shaky ground to start with.
This is actually a theme that sort of reoccurs through all of the research that's been done on infinity. The idea that even some mathematicians are a little bit uncomfortable with this whole idea and aren't sure whether it really should be used practically.
There have always been mathematicians who've been uncomfortable with infinity. I think it's fair to say that these days they're few and far between, but certainly up to the early 20th century, there were still mathematicians who were suspicious of anything other than whole numbers and ratios. They could just about cope with irrational numbers, but infinity certainly they felt was going beyond the pale to make any practical use of it.
You're listening to Skeptically Speaking, and we'll be right back with Brian Clegg to talk more about the theories behind infinity after this.
On the next episode of Skeptically Speaking, we're looking at some common assumptions about healthcare, including the well-known benefits and less discussed costs of popular screening technologies. We're joined by drug policy researcher Alan Castles to talk about his book, Seeking Sickness, Medical Screening and the Misguided Hunt for Disease. And we'll speak to paramedic and skeptical blogger Michael Cruz about Bad Science Watch, a new nonprofit watchdog organization dedicated to improving the lives of Canadians by countering bad science. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for our regular host, Desiree Schell. I'm here with Brian Clegg, author of the book, A Brief History of Infinity, The Quest to Think the Unthinkable, and we're doing our very best to understand the often mind-bending paradoxes that come up around infinity. And speaking of questions, I actually have one from the website. This is from Tony T. in Westerville, Ohio.
Is there an intuitive way to think about objects that have finite volume but infinite surface? My calculus professor would say that you could fill the object with paint, but you could never paint the surface.
I guess the best known example of that is something that's sometimes called Gabriel's horn, which is a very simple mathematical function. It's basically 1 over x for every x bigger than 1, and then rotated. So if you imagine it's basically like a straight, long hunting horn, but it goes all the way off to infinity, getting narrower and narrower and narrower. And the strange thing about this horn is, as your listener says, that you can fill it with a finite amount of paint. Just pi units of paint would be enough to fill it all the way up. But its surface area is infinite, so if you tried to paint the whole thing, paint the outside of it, in theory it would take you forever. Now, in practice, the reason it's not an issue physically is that reality comes upon you really very quickly when you're talking about the infinite. And so if you imagine trying to paint it along its length, in practice you would never get there, because very soon it would get much narrower than an atom, and you'd never actually get any paint onto it. So the practical thing is not a problem. Mathematicians will tell you it's not an issue mathematically either in the mathematical world, basically because area and volume are, if you like, totally disconnected. They're orthogonal to each other, if you like. They go in different directions. And so it isn't a problem in practice having an infinite area but a finite volume. But as far as the brain is concerned, it's certainly something I think we all struggle with imagining.
This actually brings up an interesting question about how sort of real infinity is, or could possibly be to us at least. We can understand infinity abstractly in pure mathematics, and we can even use the concept to help us solve some engineering problems. But is infinity a real thing? I mean, we can't really divide something physically up into infinitely small pieces, can we?
Really, all the way back to the ancient Greeks, this is something that people have thought about. Aristotle said that infinity was a potential. And what he meant basically was that it's something that in principle could exist, but in practice doesn't. And his illustration of it was actually quite good. What he said was, imagine something like the Olympic Games. Everybody would agree the Olympic Games exists, but I can't show you the Olympic Games, because they don't exist, at least certainly not here and now. As it happens, they will exist fairly soon in London. But generally speaking, at any particular time and place, I can't show you the Olympic Games. But they do exist. And then infinity is a bit like that. I can't show you infinity, but it does exist. And it has the potential to exist. And it's really this potential infinity that we use in calculus. And the way they got round the problem of dividing 0 by 0 was effectively saying we'll take smaller and smaller and smaller units, but never take them all the way to 0. So we never hit that problem. They'll just be as small as we need to work anything out. But does real infinity exist? Well, frankly, we're not sure. Physically, the chances are you can't divide things up forever. Most physicists, I think, would now agree that there is a certain size, the Planck distance, beyond which physical space breaks down. You just can't get smaller than that. But whether the universe is infinitely large, we certainly can't say. Throughout the history of science, people have argued about this, and it's gone from people thinking it's infinite to thinking it's not, and back again. And at the moment, we know that the visible universe has a fixed size. We know roughly how big the visible universe is, but whether or not there is something going on beyond that forever, we really don't know.
I have another question from David in Springfield.
Do people have a problem accepting or understanding infinity only because of our cultural predisposition to a Platonic view that isn't compatible with the concept? And should this change?
I'm not totally convinced about that. I have to confess, I'm not a philosopher. I don't know the subtleties of sort of difference of thought between, say, Aristotle and Plato. But I would have thought, given that I think Plato, and Aristotle, a lot of the ideas overlap, that the concept of potential infinity was not one that would not fit within a Platonic worldview. And in the end, I think the concept of infinity, that when we're talking about maths, is slightly different from the concept you might be thinking of if you're thinking about the infinite in, say, a theological sense or something like that.
So to wrap our heads properly around the mathematical concept of infinity, we really had to first wrap our heads around sort of the underlying fundamental concepts of counting and numbers themselves. And the first person to create a formal theory for this was a man named George Cantor, who came up with set theory. What is set theory, and how does it relate to infinity?
Well, a set is really just a collection of anything. So it could be a collection of objects that have a particular color. It could be a collection of everything you've thought of today. A set is just any form of collection of things. And in a sense, it's the fundamental of arithmetic. It's the way arithmetic is built. And what Cantor did was really to establish that you could build all the basics of arithmetic, and from that mathematics on this very simple idea of a set, how many things there are in it, how those things are related. And the interesting thing about set theory from the infinite viewpoint is particularly one concept which is called the cardinality of the set, and that tells us how big a set is. And so, for instance, I can say if two things have the same cardinality, I can pair the things in the sets off. So imagine, say, I've got the legs on my dog, and I've also got the horseman of the apocalypse. I think that's an example I've used before. And what I can do is pair off one leg with each of the horsemen. And if I do that, they're all used up. So I can say they have the same cardinality. Those sets have the same size. And the interesting thing is I can do that even if I don't know how many legs a dog has. As it happens, I do. It's 4, but I don't have to know that. I can say they have the same size. And that becomes really important when you start comparing infinite sets. Because obviously we can't actually count all the things in an infinite set, but what we can do is see if two infinite sets have the same size. And from that, Cantor really started thinking about some of the really incredible things that are possible when you start manipulating infinity, that perhaps you can go beyond infinity and come up with something even bigger.
What I really find fascinating about the idea of sort of levels of infinity is the idea of one infinity being bigger than another. But this idea is really tricky because some intuitive ways we might sort of categorize one as bigger than the other actually doesn't work. So, for example, it seems sort of logically that there should be more whole numbers than there are squares, but that's not actually the case, is it?
This was actually something that Galileo came up with. It's another of the examples he used to fool poor old Simplicio in his book, and he gets very confused about it, because Galileo basically says, you know what numbers are and you know what squares are, and think of any number, you can come up with a square for it. So basically there is a square for every single number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. You can come up with a square for every single whole number. And that's fine. So it seems like there are the same number of squares and whole numbers, but actually, of course, there are lots of whole numbers that aren't squares. So where 1, 4, 9, 16 are all squares, all the numbers between that, 2, 3, 5, and so on, aren't squares. So actually, in one sense, there are more whole numbers than there are squares, but there's one to match with each one. And this is one of the confusing aspects of infinity, is that you can actually have a set, which, if you like, would be all the squares, which is a subset, so it's part of another set of all the numbers, and yet they're both the same size. They both have the same cardinality, this measure of size, because I can pair them off. I can pair off the square with its number all the way through to infinity. So we basically say those sets have the same cardinality, even though one appears to have more items in it than the other.
But there are actually different levels of infinity as well. For example, I believe the irrational numbers.
That's right. Cantor came up with a wonderful proof of this that requires no math at all. And his idea was basically, let's imagine writing a list of every single number between 0 and 1, say. Now, obviously, it would be an infinitely long list, so we can't actually write the whole thing. But you could imagine starting to write down a list of every number between 0 and 1. And if I could do that, then I could pair off, just as I did with the numbers and the squares, I could pair off the whole numbers and every number between 0 and 1, every fraction, every decimal that comes between 0 and 1. But Cantor proved very cunningly that you just can't do this. Now, I must admit that this proof is much easier if you can actually see what's going on. It's a bit of a difficult one on radio, but what he basically did was scramble up all the numbers in this list between 0 and 1. So you had a totally random set of numbers in this list. And what he did was said, okay, look at the first number and we'll take the first decimal place and we'll just add 1 to it. Take the second number, take the second decimal place and add 1 to it, and so on through the list. And then what you do is extract those decimal places and you've formed a new number. And the interesting thing is that new number isn't in your original list. It can't be the first number, because it's different in the first decimal place. You added 1 to the first decimal place. It can't be the second number because it's different in the second decimal place, and so on all the way through the list. And what he effectively did was to prove that you just can't make a list where you compare off each of the numbers between 0 and 1 with the whole numbers. you can't pair them off because there's always going to be extra ones that you just can't fit in the list. And again, it gets quite mind-boggling, but if you see this drawn out, it is actually fairly convincing that there just has to be a bigger infinity in the numbers between 0 and 1 than there is between all the counting numbers.
Now, as I understand it, poor Cantor didn't exactly make it out of this foray into the infinite unscathed, did he?
I think I've probably said on the cover of the book something like it drove him mad. That's a slight exaggeration, but certainly he did suffer from mental issues, and it's thought that one of the reasons for that was just the challenge of sorting out certain aspects. There was something called the continuum hypothesis, which basically was trying to work out whether this infinity of all the numbers between 0 and 1 was the next biggest infinity than the standard infinity, if you like, than the infinity of the counting numbers. He never managed to prove this, and that was one distraction. Another problem, frankly, was there was another mathematician called Kronecker, he was one of these guys who really hated the idea of infinity, and he made it his life work to ruin Cantor. So he stopped Cantor from getting appointments in other universities. He stopped him from getting stuff published. And it's probably Kronecker's opposition that was the biggest factor in pushing Cantor over the edge.
And Cantor wasn't the only mathematician who studied infinity who went a little bit insane. There was another one, wasn't there?
Well, Kurt Gödel is the other one, I guess, who certainly had some serious mental issues. Gödel would actually, in some ways, help resolve the problem that Cantor had, although in a very unsatisfactory way, because what Gödel did was come up with a way of proving that there are some things in maths that just can't be proved. He basically said that in any system of mathematics, there is always going to be something or some things that it is absolutely impossible to prove whether or not they are true. And it turned out that with set theory, it is actually impossible to prove this thing that Cantor was trying to prove, the continuum hypothesis, the idea that his infinity of everything between 0 and 1 was the next biggest infinity than the basic standard infinity, as it were. It just was not possible. And Gödel really was a very strange guy. Towards the end of his life, he was convinced people were trying to poison him. He wouldn't eat anything unless his wife had tasted it first to make sure it was safe. And basically, when his wife died, he himself died of starvation because he wouldn't eat things. So, yes, he had serious problems, although, again, probably wasn't infinity itself that totally pushed him over the edge.
I'm thinking maybe thinking about infinity probably didn't help him very much, though.
That's true.
So you talk a little bit near the end of your book about something that I've read a little bit about, which is quantum computing, which is trying to use sort of quantum theory and this idea of infinity in a sort of real way to make better and faster computers.
Quantum computing, if it is possible to make it practical on any scale, and I believe it will be certainly within 10 to 20 years, really uses infinity in a kind of practical way. And the way it does that is that instead of using a conventional bit, so an ordinary computer uses a bit that can either have the value 0 or 1, and that's it. In a quantum computer, the bit is replaced with what's sometimes called a qubit, a quantum bit, which is actually a particle, which might be a photon of light, or it might be an electron, but it's an actual physical particle that is acting as the bit. And what's used is one of the properties of that particle, say perhaps its spin. Now, the peculiar thing about quantum particles is that if you measure the thing that's called the spin of the particle, it's not really quite the same as something spinning around, but it has some similarities. It can only have one of two values. So if you measure it in a particular direction, it will either, say, be up or down. It can have nothing in between. But it's not just straight up or down, it's basically up with a certain probability, down with another probability. In a sense, it's in both states at once. It's the quantum weirdness, I guess, of this particle, is that it can be in both states at once with different probabilities. And effectively, you imagine if something has two different probabilities, one, say, of being up, the other of being down, that's the equivalent, if you imagine, of a sort of arrow that points somewhere between those of a particular direction in space. So the more up it's got, the more that arrow points up. If it was 50-50 up and down, that arrow would be sideways. If it was more down, then the arrow would be starting to point down. And by having different values for those probabilities, effectively what you've got is a real number. So to define the direction of that arrow, you have a number, that could be 0.5137, whatever, all the way to infinity. So effectively, one of these quantum bits can handle a real, whole, infinitely long number. And that gives them the potential to calculate in a totally different way. And if you have the right software, and strangely, some software has already been written for quantum computers that can do quite amazing things. For instance, one's been described as finding a needle in the haystack. It's basically a way of searching for things where an ordinary computer would have to do 1 million tasks to find it, potentially. This will find it in just 1,000. So it's speeding up vastly beyond anything we can do at the moment. At the moment, practical quantum computers are very small. They only have a few qubits in them. They don't last for long because those qubits decay. But I would say within 10 to 20 years, we could have computers that were vastly beyond anything we can imagine at the moment because of that.
I know I, for one, as a regular computer user, am always excited about the idea of faster computers.
It's not just speed. They can actually do things that are pretty well impossible, that would take any ordinary computer longer than the lifetime of the universe to calculate because they're working in such a different way. They're limited. They can't do everything an ordinary computer can do. But for these special types of calculations, another thing they can do, incidentally, rather worryingly, is break the encryption that's used to do things like when you use a credit card on the internet. Uses a form of encryption that works effectively by working out from a very large number what two prime numbers have been multiplied together to make that very large number. Ordinary computers find that quite difficult to break, but a quantum computer, again, there's already been the algorithm written, effectively the theoretical software, that would enable it to break that trivially. So if anybody ever did get a working quantum computer going, we would probably have to change all the security on the internet, which is a bit frightening.
That is a little bit worrisome. And we're unfortunately all out of time. Brian, thanks for joining us today.
Thank you. It's been good fun.
If you want to learn more about Brian Clegg and his collection of most excellent science and math books, you can visit brianclegg.net or visit skepticallyspeaking.com, where a link to his website will be available in our show notes. And while you're on our website, we'd love it if you'd click on over to our Facebook page, visit our Google Plus feed, or follow us on Twitter, where you can keep up on all the latest news and updates. You can also visit Skeptically Speaking on iTunes, where you can subscribe to the show and download all of our past episodes. Thanks for listening to Skeptically Speaking.
Before we go, I want to let you know about a fundraising drive that one of our team members is working on to raise money for the Muscular Dystrophy Association. Our producer, K.O. Myers, is participating in an executive lockup. He'll be spending an afternoon pretending to go to jail to raise money for the fight against degenerative muscle diseases that affect millions of patients and their families every year. He's asking for donations towards his bail, and there's an easy way that you can help out. Anytime between now and August 16th, you can go to KO's donation page and pitch in to help him make his fundraising goal. Your donations will support the Muscular Dystrophy Association, and MDA is a nonprofit health agency dedicated to curing muscular dystrophy, ALS, and related diseases by funding worldwide research. The association also provides comprehensive health care and supportive services, advocacy, and education. You'll find the link to donate in the show notes of this episode, which is 172, on our website at skepticallyspeaking.com. Please donate if you can, and do help out by sharing the link with your friends. Thanks for listening.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell, gonna raise a little hell, break the spell of Pavlov's spells. Cause we're skeptically speaking, our mind reading tarot cards and witches, psychics, and their spoon-bending mind tricks. All the humbug, flim-flam, frauds and shams, the charlatan woo. I don't think you understand, it's the hocus pocus, out of focus locus, eroding the brain, making gains on the hopeless. Let the crystal ball fall, smash on the floor, leave the pieces alone, we don't need them anymore. Just a micro microscope, telescope, magnifier, reading in between the lines of these lies. Bring it on, the skeptics await your letter, your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is, 'cause we're skeptically speaking.